Which of the following is an example of a quantitative observation? The difference between quantitative and qualitative. Quantitative always has a number and a unit of measure. Qualitative is general descriptive term, like what color is it? Is it big? Is it heavy? Comparisons. This one's longer than that one. This one's heavier than that one. Those are qualitative. Quantitative has a number associated with, like I said earlier in our first discussion, I'm 71. Am I 71 inches or 71 years? If I give you a unit, then that's a quantitative measurement. 2, generally observed behavior. I better write these up here as I go. Sometimes the recording is a little faint. It should be 1080p, the recordings. So they're going to be a lot easier to see the details. Generally observed behavior that can be formulated into a statement, sometimes mathematical, is called what? A what?
Natural law.
Natural law, yeah. Yeah, natural law. Doesn't say anything about why this stuff happens. That would be a theory. This one is a natural law. Okay, let me see, can I do this without going to the computer? Order the 4 metric prefixes from smallest to largest. You gotta know what the prefixes stand for. The way I solve problems like this, where you have to put things in order, is I nail down both ends and then I fill in the middle. So which one is smallest to largest? Which one's the smallest of those 4? Each one's got the same prefixes in it. They're just ordered differently. So which one's the smallest? Nano, yeah. So now you can eliminate. Actually, that's all you need. I should have put another one in there with nano over here, right? Then you'd have to think about it. But this one, nano says that's the smallest, and none of the others fit. So test taking technique, you're done. But this is, what is a nano? It's a billionth. 10 to the minus 9th. Milli, 10 to the minus 3rd. Thousandth of. Centi, a tenth. And kilo is 1,000 times. So that's obviously the biggest one. Okay, what's next? On the list. 6 and 7. Sit back. There we go. 6 and 7. A kilogram contains how many grams? Oh, excuse me, 8.1 kilograms. I ran these together in my eyes. 8.1 kilograms is how many grams? When I have a problem like that and I want to go to a base unit, I just take this. What does that mean? That means 10 to the 3rd, right? So these are equal. 8.1 times 10 to the 3rd grams. This one. The other way you can do it is dimensional analysis. If it's not that obvious, it's not that easy, then if we want to go from this one back to that one, how about that? You need a conversion factor, right, that gets rid of grams and leaves kilograms, right? So this is numerator, denominator. So what's the equivalence? 10 to the 3rd. So you divide 10 to the 3rd into 8.1 times 10 to the 3rd. Those cancel too. So you're back to 8.1. This time it's kilograms because of that. So there's more than one way to solve these problems. Let's say 7. Yeah, look at 7. Convert 0.390 meters to millimeters. 3980 meters to millimeters. Okay, So if we're going to extract milli out of this, we need to pull out 3 to the right. Excuse me, that's not right. I'd rather use dimensional analysis. You need to know what the prefixes mean, but sometimes they can get you in trouble. If you think you know and then you do it wrong. Usually what you do is you go the wrong direction. And instead of 1,000th of, you go 1,000 times. So dimensional analysis always keeps you out of trouble. Meters to millimeters. Okay, so 1,000 millimeters in a meter. There you go. So the meters cancel and you get 1.3980 millimeters, excuse me, times 10 to the third millimeters. Then you look at your answers. Right? Well, you got a mix. Right? So nothing matches this one. So let's make scientific notation out of this. Okay, is that one in there? No. Now, there's standard notation. So let's convert it to standard. 2 places. There we go. 398 millimeters. There it is. Right there. And if you do this stuff enough, you'll know that if you want to go to millimeters, how many? If this is meters, here's another rule that will, it's kind of an estimation rule. If the unit of measure gets smaller, then the number gets bigger. So if this one gets smaller, down to millimeters, then this one has to get bigger. So that informs you as to which direction to move your decimal. So this one's 1,000 times difference, 1, 2, 3. So that would have got us there quicker. Dry. Prime it. 7, 9. Next one. Oh, too far. Scroll a little bit. So go right now. What's the measure of resistance an object has to change in its state of motion? What's the definition? The measure of resistance. Now, there's another word that describes what's happening. Anything that resists, this is Newton's first law, anything that resists a change in its motion or causing it to move from a position of rest, it's called inertia. But that doesn't measure anything. Mass measures that inertia. Okay. Right. And 11. Now, I wish this pointer had a scroll bar on it instead of just a page changer. As part of the calibration of your new laboratory balance, a 1 gram mass is weighed with the following results. Okay, so what that means is that 1 gram mass is our standard. That's the true value. But our balance tells us it's 1.2, 1.2, 1.2. What does that say about its accuracy? It's not accurate. Okay. How about precision? How do we tell precision? We compare the multiple measures. And they're only 1,000th off each one. They're to the 1,000th position. That's precise. So it's not accurate. Let's see. It's precise, but not accurate, inaccurate. Now, you may not have seen this before. When it says plus or minus 0.001, that's a confidence interval. Now, it doesn't, it's missing information because a confidence interval needs to say how confident. In statistical terms, typically you're 95% confident of the interval. So if it doesn't say what the interval is, it's not 95%, you assume it's 95%, unless they say otherwise. They usually don't go down. Sometimes they go up, like 99%. But this is generally 95%. So between those two numbers, so what's the average here? It's 1.201, isn't it? Of those three, 1.201. Plus or minus 0.001. So plus would be 2 and minus would be 0. So all three of those are within the interval of the average. I didn't write those numbers in there, if you're puzzling about it. Yes, I should. So if this is the average, this is plus, and this is minus. Okay, that was 11. 12 and 13. So we're going to use our target practice. Which of the following figures represents a result having high precision? High precision simply means tight group. So the tightest group here, well, this one is a tight group and that one's a tight group. So 2 and 3 here, that satisfies that condition. Which of the following, and then which of the following statements concerning these figures is correct? So now we've got to read through each one. Figure 1 represents systematic error and figure 2 represents random error. Okay, what's the difference between systematic and random error? Versus random. Right. Systematic error is error that occurs the same way every time. And it's the good kind of error, if you can say that, because if you know how it's going to happen each time, you can correct for it. If you know that your thermometer reads high by 1 degree, you've checked it against a standard, then each time you use it, instead of saying 98.6 degrees Fahrenheit, it might say 99.6 body temperature. Well, it's Celsius, 37 degrees. So it might say 38 degrees. You know it's 1 degree high, so you read it as 37. That's the good kind of error. Random error is error you have no idea where it comes from. You may have a suspicion, but you don't know it well enough to call it systematic. Sometimes we don't have a clue what's causing random error. So that's when statistics comes in. And statistics helps you minimize the effect of error. Or it also helps you look at your data set in such a way that you don't make erroneous or wrong conclusions. It's supposed to keep you honest. So random error just goes all over the place. There's no explanation for it. All right, so let's look at these and see. Figure 1 represents systematic error. Is that systematic? I don't think so. Figure 2 represents random error. Actually, high precision, but not accuracy is systematic error. It's used the same way every time. If you were zeroing in your scope and you got this, that would be good because now you can correct it. You can dope your scope and bring everything back down here. So that's systematic error. This is random error. Bad precision is random error. So A is wrong. How about B? Figure 1 represents random error. Figure 2 represents systematic. That's true. And since there are no two of the above, one of the above, none of the above, any of those weird statements down here, you can stop. You got the answer. So, summarize. This is systematic error is owed to precision. If it's got high precision, then it can be wrong, but we know why it's wrong, and we can correct for it. A random error is low precision. All right, what do I have marked next? 16. Over here. With my hand. All right, the amount of uncertainty in a measured quantity is determined by the amount of uncertainty. What determines the uncertainty of a measure? Well, basically two things, the instrument and the operator. There are very few measuring devices that operate completely autonomously. Maybe on some of our robotic spacecraft, you might consider those autonomous, but still, they receive instructions from Earth. And they execute the instructions as given. So if your instructions are wrong, then the operators are at fault for the error. Okay, so that's A. Both the skill of the observer and limitations of the instrument are responsible for uncertainty. 17. A scientist obtains a number 04500 6700. Okay, on the calculator. Like I said before, calculators give you as many decimals as you want. They're not smart in the way that we want them to be. So your calculator gives you this, but you're limited to 4 significant figures based upon what? The rules of calculation: addition, subtraction, multiply, divide. So you know that you're limited to 4. So where do you start? Well, these two are not significant, correct? So we start here. 1, 2, 3, 4. So we're aiming at that one. So how do we round? We look to the one right to the right of it. That's greater than 5. That means this is 1, 0, 5, 4. 04501 is your answer. 4 significant figures. Zeros to the left are not significant. Captive zeros are significant. And in fact, that 0 is significant also. Okay, how about these? Are those significant? Yeah, they're to the right, but there's an explicit decimal. That means they're significant. Okay, so how would we write this number in scientific notation? Okay. And that keeps all your significant digits in the coefficient. All right, 17. Let's give 18's repetition. Go down to 20. Can I do this? Oh, almost got it. Scroll a little bit. There we go. Express this number in scientific notation. So we have 0810. Right, so we need a number between 1 and 10. 2 to the right, When we keep that 0, it's significant. The reason I know this is a negative, I moved it 2 places, but is it positive or negative? Well, it has to be negative because I'm taking a small number and making a larger number. So as that number gets larger, the power of 10 has to get smaller. (21), 2, and 3. There must be some difference. 21. Oh, we'll go backwards. 6.49 times 10 to the minus third. They want that in standard notation or common decimal form. All right, so we take this, and if this is small, then the overall number has to get smaller than this. So we're going to move it. Let's put some zeros out here. Go 1, 2, 3. Just stop me if you have questions. Let's see, 22, I said. Express this number in common decimal form. Well, okay. This time, we move the decimal in the other direction. 2.37 times 10 to the 4th. Right? So we need to move it to the right. 2, 3, 7. There's some zeros out here. So it starts here and goes 1, 2, 3, 4. Now, that's where we would put the decimal. The problem is there are no significant digits out there. So we have to get rid of these and the decimal. Because we can only have 3 significant figures in our number. Those 3, these 3. And there it is right there. I should have put one in there with put a decimal and a couple of zeros out here. That's a trick. Go to 23, I think. I'm going to do 3. Yep. About the next page. So I'll scroll down to catch 24. Yeah, can't go far enough. We generally report a measurement by recording all of the certain digits plus how many uncertains. Just for example, if I write that, these are certain. This one is uncertain. That's by convention. We always write numbers that way. Now, if we write it that way, 1, 2, 3, 4, 5 significant figures here, which gives us 4 certain and 1 uncertain. But they're all significant because they're all non-zero. So that's what? B. 23, 24. Can I do this? Yeah, there we go. 24. Okay. Word problems. Everybody loves word problems, right? You're asked to determine the perimeter of the cover of your textbook. You measure the length at 39.36 centimeters and the width at 24.83 centimeters. How many significant figures should you report for the perimeter? This is the perimeter of your textbook. 39 centimeters. How many centimeters in a meter? 100? Oh, so that's a third of a meter. Okay, maybe that is correct. Let's have to do estimation in my head. Okay, we're doing the perimeter of this textbook, correct? Right. Sometimes it helps to draw a picture. 2483 on this side and 3936 centimeters on that side. So if we're doing the perimeter, what type of operation is this? Add, subtract, right? So we're going to add these two together and those two together and everybody together. So we need this one, this one, this one, and this one. Just add them together, right? So 3 6 is 18. And then 16, 17, 23. And then 11, 20, 28. 2, 4, 6, and 6 is 12. So this is, what are our units of measure? Still centimeters, right? Because we're just adding centimeters all the way down. Okay, how many of these can we keep? All of them, right? Here. There's the decimals lined up. These are all significant. Significant, get to keep those, that one, that one, that one. So the answer actually has 5 significant figures. That's what's tricky about the add subtract rules. You can't tell what the final answer is for numbers of significant figures until you actually do the calculation. Sometimes it'll come out more than you expect. Like you start off with 4, you end up with 5. Sometimes you start off with certain numbers, you might start off with 4 and end up with 3. So you just have to do the calculation to see what it is. Not like add, multiply, divide. You can determine that one. Just look at the smallest significant figures and you can answer that one quick. So 5. Right. I get 4 a lot on this question. Because they forget the rules that they're going by. You draw a picture, that helps a lot. We didn't ask for the area, we asked for the perimeter. If we'd asked for the area, yeah, you'd be limited to 4. Because you multiply height times width. But that wasn't the question. 26. 26. Let's scroll by hand a little bit here. Okay, significant figure rules for 26. You got this number, and you got a mix of add, subtract, and multiply, divide rules. So fortunately, you're given parentheses, right? So if you follow the rules, always do parentheses first. So we would add 6.167 and 68. Like that. All right. There you go. And when you're mixed like that, you have no choice. You've got to round this one first. Two significant figures, 74. Now you divide by 5.1. And you can only keep 2 significant figures in the answer, which is C. Probably had to round. All right, 26. 27. There it is. Okay, for this one, it's just a straight subtract rules. So you line up the decimals. 179. There we go, subtract. Is that right? Yeah, that's right. Okay, so how many can we keep? Right there. 3.823. Okay.
Why is it 4?
I'm sorry?
Why keep it to 4?
Oh, because it's a subtract rule, add subtract rule. You line up the decimals, And then you're limited to the number of significant figures to the right. So this one goes out to here, you have to stop there. You can't go to that extra one because it doesn't have one here. All right, 27, how about, let's get 28. Go to 32. 32 is complicated. Yeah. In this case, we have parentheses to help us. Let's see, 32. And, well, rather than write all that stuff up there, what does PEMDAS say? Parentheses first, so we have to do this one first. And then no exponents, multiply, divide, so that means whatever we get here, we divide by 2, and then we subtract. Okay, so let's do that. 3.47H times 1.164. Now, when you got a sequence of multiply and divide, before you get to any add subtract rules, I prefer to keep all the decimal points until the end of the multiply divide sequence and then round. So I've got this long decimal here, and I'm going to divide it by 2. Okay. Now I get 2.024196. All right, but in the process, I'm limited to 3 significant figures. So now I have to round right to here. So those go out, and we have 2.02 minus 0.169, minus 0.169. So 9 from 10 is 1, 6 from 11 is 5, 1 from 9 is 8. So we're limited to 2 decimal places here, right there. 1.85 should be it. Okay. Let's see. There it is. One click. 35. Express the volume 781.2 cubic centimeters in liters. 781.2 cubic centimeters. And we want liters. 5. Okay. What's the trick here? Cubic centimeters is milliliters. Now we can convert to liters. Right? 1,000 milliliters in a liter cancels. We just divide this by 1,000, which means 7.781. Now, why can I keep all these? Because that's a conversion factor. It's infinite significant figures. Good. Forgot my unit of measure. Okay, 35. And let's go down to 37. All right. The pressure of Earth's atmosphere at sea level is 14.7 pounds per square inch. What's the pressure when expressed in grams per square meter? This is going to require chain conversion. Oh, let me move on here. 14.7 pounds per square inch. Okay. When you have something like that, and you've got to convert both top and bottom units, well, actually, if you have more than one out here, do one at a time. So the conversion factor I want to do is convert pounds to grams first. So do we have that available? We have 2.205 pounds per kilogram, okay? So we can convert pounds, let's see, 2.205 pounds. 2.205 pounds equals 1 kilogram. Got rid of pounds. Now we went from the English system to metric system. We're going to convert that to grams. Kilogram to the third grams. Now we got the grams. Next, we're going to convert square inches. So 2.54 centimeters equals 1 inch. So 1 inch equals 2.54 centimeters. This one's squared. What do I do now? Square the whole thing. Okay. That means this squared, that squared, divided by this squared, that squared. That's the rule of exponents. So we got that one done. And this is going to be squared once that is squared. So don't lose track of that too when you're doing your calculation. Okay. So we've got square centimeters. Is that what we're after? No, we need square meters. So let's convert centimeters to meters. Right, 1 meter equals 10 squared centimeters. Square it again. That gives us square meters. This is square centimeters, cancels this square centimeters, and we're done. We've got grams per square centimeters, square meters. Now, that's the thinking part. The rest of it is number crunching. You have to be careful with these, especially when you introduce these powers. When you do your calculations, be sure and get those done. If your calculator is not as user-friendly as mine, then you may have to do these individually. Like square that one and put that number in here. Now this one's going to be 10 to the 4th. But that one might give you trouble if you forget to do it. So if I say 14.7, and then I usually go across the top and then across the bottom. That's 1, that's 10 to the 3rd times this number, and then 1 squared times it, and then 10 to the 4th times it. Okay, now I come back and divide. 2.205, and then 2.54 squared, and then divide that. And then 1 divided into that. So I get 1.0, wait a minute, how many significant figures can I have? Well, these are all conversion factors here. So you limit it to the original, 3 significant figures. 1.03 times 10 to the 7th. Grams per square meter. There it is, B. Did I lose anybody? It starts sounding like I'm an auctioneer. Walking too fast. The whole point of doing this is to be sure you know how to convert multiple units. This one, it has units in the numerator and the denominator. So you do one at a time. I went pounds first. I went pounds until I got to grams. That was done. Then I go back and do square inches. I know this relationship of centimeters to inches, but I don't know off the top of my head square centimeters to square inches. Okay. So I just use the linear relationship and then I square it. Works every time. And then I have to convert that also. So that's the thinking part. The rest of it is be sure you know how to run your calculator. $37. Let's see what's next. We're going to skip into a bit. We'll do it on time. 145. Okay, I need to get blue on it. Let's see, 41 is changing density. That's a paired unit conversion also, so we're going to do that. We just did one just like it. 46 is okay. I'm not even out of chapter 1 yet. I don't want to eat into your lab time. So I'll tell you what. There's some. I give you the numbers that I was going to do. 2 or 3 on those. Somebody zooming in. Yep. Randy Tucker. I got you.
Sorry, I'm late.
You do know we're having a lab today.
Mm-hmm.
There's nothing you can do about that right now. Okay, I was going to do 46, 49, 50 and 51. Let's see, 54. Let's stop when I get more than that. About 56. We'll do 56. This takes a little bit of thinking. Has anybody done 56? You'll tell me how to do it. No. Okay. A monolayer containing 3.23 times 10 to the minus 6 grams of oleic acid. Has an area of 20.0 square centimeters. The density of oleic acid is 0.895 grams per milliliter. What's the thickness of the monolayer? They say it's a monolayer because it's only got one molecule thick. And the reason we know it's that way is because water is like this. Water is the oleic acid molecule has an acid end and it has a long hydrophobic tail. So the tail goes up here like this, and then this carbon and the acid attract to water. So they go in there and they stand up on their end like that, all the way across. So if you know, if you give these facts, then you can determine how big that molecule is. All right, so how do we do that? Well, you need a pan of very, very calm water, and then you need to dust it with talc. Okay. Then you calibrate a dropper, like you do maybe 20 or 30 drops, and then you find out what the weight is. So now you know the mass of the oleic acid that you're going to do with 1 drop. Right, so that's where they got this. That's where they got this value here. They knew that 1 drop of oleic acid was that mass. And then when you drop it here, it spreads out in that single layer. Okay. So we know, say it spreads out all the way to this perimeter. The area of this is 20.0 square centimeters. All right, what if you turn that thing up like this? What do you got? And then you got a cylinder. So what's the volume of that cylinder? Well, it's the area times the height. Right, so the volume equals the area. Area times the height, and the height is the size of the molecule. So can we figure out, we know the area, it's already given, right? 20 square centimeters. What's the volume? Density equals mass divided by volume. We got the density, 895 grams per milliliter, which is cubic centimeters, is equal to the mass, which is 3.23 times 10 to the minus 6 grams divided by volume. So the volume is going to be in, this is canceled that leaves you with cubic centimeters. So cubic centimeters goes here, then you divide by this value, that gives you the height of the molecule. So we can combine that all into one equation. All we have to do is say we're solving for height. So let's say height equals volume divided by area. We know what volume is. Volume is equal to mass divided by density. So that volume is equal to mass divided by density. So we just plug in the values we know. We know area, we know density, we know mass, we got height. Got the size of the molecule. If you do those calculations correctly, you should come out with this many centimeters long is the molecule. Okay, 56. Let's see. I was going to do 57. Let's see, 58. Uh, 62. 70 through 73. I'm going to run out of time. We're not even going to make it to chapter 2. What I'm going to do is, once I get you guys started in the lab, I can come back and you finish chapter 2. We're going to record it.
Another hour. I just started the lab.
Let me see. I'll tell you what. I'm going to look at chapter 2. Let me tell you which other ones I was going to do. Then you can at least look at the work problems, see how I did it, because I'm going to do it the same way on board. 72, 75, 80, and then we're chapter 2. So chapter 2, I was going to do 1, 2, 3, and 4. 1 through 3, you just need to know who's responsible for each one of those statements. Chapter 4, you actually have to know the difference. Let's see, chapter 2. Number 4, did I say? Yeah, which is defining pairs of compounds. All right, so we scroll down. Which of those 4 pairs demonstrate the law of multiple proportions? Remember that one? Multiple proportions. That was Dalton. He said that when you have a compound with 2 parts to it, if you hold one of them constant, then the ratio of the other parts are whole numbers. Right? So it would be like this, like this. So which one satisfies? Well, A has to be the same on both sides. So A is the same here, but there's no B here. Zinc's okay, but now we got oxygen and chlorine. That won't work. How about this one? Hydrogen's okay, but that one's oxygen, chlorine, nitrogen, and then oxygen. That one works right there for multiple proportions. That is often confused with Proust's law of definite proportions. So don't get those two confused. Let's skip to 7. Okay, we'll do 7. Oops. We might run over a little bit. I think we can stand it. I've already got the water started boiling. Just won't have to wait for that. A sample of chemical X is found to contain 5 grams of oxygen, 10 grams of carbon, and 20 grams of nitrogen. Okay. If the law of definite proportions would predict that a 70-gram sample of this compound, 70 grams, would contain how many grams of carbon? So this is the one we want right here. Well, what are the ratios here? It's 20, 30, 35 total. If we look at that ratio, that total, right? So this is double. We actually double the mass of our X, so we'd have to double the mass of this. So we have 20 grams. Let's see, did I put too many? There, 20 grams. So we're getting a little lax with our significant figures and decimals. But that's the best answer. That's my rule. If you don't find the exact answer, pick the best one. Now, if there's one in there that says none of the above, and you're off by just a decimal fraction, then you're within your rights to say none of the above. It's not exact, and you can prove it to me. Right? Show me your calculations. All right, calculate this way, and if I say, okay, that's good, all right, the other point. Oops. We're in chapter 2 now. Okay, let's see, 11, that's definition. 12 definition, 13 definition. 14, 15, 16, 17, 20. Let's do 20. There we go. Which of the following atomic symbols is incorrect? All right. So you need your periodic table. Right? You got to find out how many protons in each one. 6 carbons is correct. How about the 17 chlorines? Yep, 17 chlorines. How about phosphorus, 15? Yep, that's true. 19 potassium, that's true. 8 nitrogen. Nope, nitrogen, 7. So if you just go down looking at these, you really can't tell based on the mass number, right? Because of different isotopes. But if you can't match up the symbol to the number of protons, the atomic number, then it's wrong. If you know the symbol, you know the number of protons. If you know the number of protons, you know the symbol. They're joined at the hip. So that's why E is wrong. And it's important to read the question thoroughly. Incorrect. If you read too fast, this is not a speed reading contest. Pay attention to details. All right, that was 20. 21. Let's get that. 22, which is the following represents a set of isotopes. How do you tell isotopes for 22? We don't even have to look at it. First of all, to have a set of isotopes, you need the same number of protons, right? So 1 and 4 satisfy with different neutrons. 2 and 5 satisfy with different number of neutrons. And 3 is left out. It's got no match, right? There's nothing in there with 22. Oh, excuse me, it's backwards. Well, there's nothing in there with 18 protons either. Ooh, that was tricky. You're looking at protons in the first place, and then all of a sudden I throw in neutrons first. It almost caught me. What's the saying? Hoisted on my own petard. That's from the medieval days. Okay, 22. Let's see, skip down to 28. How to calculate an ion? There, 28. So a species with 12 protons and 10 electrons. If it's got 12 protons, we know the symbol should be in magnesium. Oh, with 10 electrons, what's the charge? It should have 12 electrons neutral. But if we lost 2 of them, that means we've got an excess of 2 positives. That's the correct symbol for these conditions. There. Okay. Let's see, 29. Almost get that. 33, 34, 35, 36, 37. Well, down to 36, you're just matching symbols and names. So you should be able to do those in your sleep. Characteristics of a metal, 37. Which of these, all are the following characteristics of metal except, so one of them is the outlier. Are they good conductors of heat? Oh yeah. How about malleable? Yeah. And you can bend them and shape them. How about ductile? Ductile is a term that means it can be stretched into a thin wire. That's true. Often lustrous, especially if you polish them. Tend to gain electrons in chemical reactions. Nope. That's non-metals. Metals tend to lose electrons in chemical reactions. All right, 37, 41. Yeah, I guess we can do that one. There we go. You're given a compound with this formula, a metal with 2 chlorides. And you're told that the metal has 26 electrons. Okay, that's it. We want to know the identity of the metal. What element is it? You know the chloride, if it's a metal and non-metal, chloride is going to be charged. And it's going to have a 1 minus charge each, which means 2 minuses total that have to be balanced by this metal. That means it's a 2 plus. How did it get to be a 2 plus? If it's only got 26 electrons, it must have 2 more protons than that. Now we can find out what it is. We just look, follow right along. Nickel. It's a detective game. 45. There it is. How many oxygen atoms are in that formula? Well, you've got 4 in this phosphate group, but there are 2 of them, right? 8 oxygens in that formula. Notice I didn't call it a molecule. Not a molecule. Molecules are covalently bound. They're nonmetals and nonmetals. This is a formula unit. Ionic compounds don't form molecules, they form crystal structures. This is the simplest ratio of calcium to phosphate in that structure. Okay, 45, let's see. 47, the correct name for, okay, let's do one of these. The correct name for FeO. All right, so you say type 1, type 2, type 3. Metal, non-metal, correct? So it's either a 1 or a 2. And then the metal is variable charge, but it can be variable charge. So you have to say what the charge is. Now we have to deduce the charge on iron. Oxygen is 2 minus, always, in ionic compound. So iron would have to be 2 plus. So we would say iron 2 oxide. Takes practice. Oh, here, what's the correct name of this right here? Well, we know that's calcium, but it's not the neutral atom, it's an ion. So we would say calcium ion. Why don't we say calcium 2 ion? Because calcium is fixed charge. It's an alkaline earth. All alkaline earths are 2 plus. Calcium 2 ion would be redundant. Okay, let's see, where am I headed to next? 51. You can do that one. Sodium dihydrogen phosphate. 53. There it is. Sodium dihydrogen phosphate. We know we got sodium, and we know this is a polyatomic ion, which says it's got 2 hydrogens and a phosphate. So what's the charge on that? The easiest way to figure the charge on that, well, you can make it out. I know that PO4 is 3 minus. If we add a hydrogen, that's 2 minus. If we add another hydrogen, that's 1 minus. So that's the formula, NaH2PO4. All right, that was 53. 56. Naming acids. All right, we'll do one of those. 56. I got 59 on the schedule too, but I'm just going to do 56. 56. I got to scroll a little bit. There we go. 56. All the following are aqueous solutions. That's important for acids, which is incorrectly named. Right, so let's look at each one. If there's an oxygen, what do we not start the word with? Hydro. No hydros with oxygen. So if we find any with oxygen that say hydro, then it's incorrect. Right. That was okay, that was okay, that was okay. Ah, that was not okay. There's no oxygen there. It should be hydrocyanic. The rest of them are correct. Sulfate becomes sulfuric. Carbonate becomes carbonic. Phosphate becomes phosphoric. And chloride becomes chloric. Hydrochloric acid, this should be hydrocyanic acid. Okay. 59. Okay. Now we've got some tables to fill in and some practice naming. You should be able to do those. I'll pick out a couple. So I got 61, 2, 3, 4, 5. Actually, all of them. All of them. All of them. Okay. It must be important. All right, so the blue is missing information in this table. And we're going to fill it in. So if you start off with PB with 206 mass number, how do you fill in the rest of them? Well, PB says that there are 82 protons. Just look on your periodic table. Atomic number, 82. It's also neutral, which means no charge and the same number of electrons. Right there, right there. Number of neutrons, you just subtract 82 from 206, and that's 124. So you got all your information right there out of one symbol. This one, gallium 3 plus, 31 is given. So it tells us that's gallium, 31 protons. Right? It also tells us that it's a 3 plus charge. So we say gallium 3 plus. Now, how does it get to be 3 plus? Because we're missing 3 electrons. So 3 from 31 is 28. Number of neutrons was also given. Oh, I need to hear that. Let's see. All right. You can do the rest of them. Let's see. This is a similar approach, like protons, neutrons, electrons, atomic number, mass number, net charge. I'm not going to waste time on that one. Write the symbol for each of these. Right? You should have those flashcards memorized by now. And then next, we write the names from the formulas. Right? You can do those. Use the rules, type 1, type 2, type 3. Process of elimination. Right? That's a fixed charge calcium, and that's a polyatomic ion. Every time you have polyatomics, parentheses. But we don't have to say what the charge is on calcium because it's an alkaline earth. It only has one charge. Down here, we're doing some more naming. Down here, we're writing the name from the formula. So let's see if there are any tricky ones in here. Silver chloride. Silver is a transition metal, but it only has one charge. So you only have to say silver chloride. You don't need to say what the charge is. What other transition metals like that? Zinc. Zinc has a 2 plus charge. That's it. No other choices. It's type 1. This is a non-metal. Like carbon and chlorine come from the right-hand side of the table. So you use type 3 rules. There's 1 carbon and 4 chlorides, carbon tetrachloride. They used to use that to clean clothes with dry cleaning until OSHA and EPA said you can't do anything because their workers were getting sick. Some of them even developed cancer. Now they have to use something a little more benign, more expensive. Okay. So we've got some more examples of writing the formulas from the names. Here's one. The reason I've answered this with 2 versions, this is the accepted version now. This one hydrogen is the acidic hydrogen. These other hydrogens are bound too tightly. They don't come loose. So that's why they're separated. But this is the acetate ion right here. So H means acetic acid. The hydro, it's got oxygen in it. It's acetic acid. This is another way to write it. This gives you a little structural information. It's the same compound, but it looks like this. Hydrogen's out here. There's your CH3 and another carbon. And then this is the double bound carbonyl. And this is OH. And there's your acidic hydrogen right there. So that's why you see it written that way sometimes. But I don't expect you to put that one in there. That's just a curiosity now. Okay. Law of definite proportions, you got that. Multiple proportions, let's see. Yeah, did mark that one, mark 88 also. 92 and 94.